It's a pleasure to have Sergei here, who's going to talk about path and magnitude homology.
I want to tell you about two different theories. One of them is called GLMY theory or path homology theory. It is a homology theory for graphs, for direct graphs. Direct graphs are called digraphs. And another absolutely different theory on the first glance, it is called magnitude theory. And the main notion in this theory is the magnitude of a metric space. And first of all, magnitude of finite metric space, but it can be also defined for compact metric spaces. And there is a categorification of this notion, magnitude homology of a metric space. And it turns out, recently people found out that these two absolutely different theories are in fact two parts of some bigger theory. All the information about magnitude homology and path homology is contained inside of some bigger, more complicated algebraic object called, which I call magnitude path spectral sequence. Okay, first let me tell you about the GLMY theory. This theory was initiated in 2012 by Grigoryan, Lin, Muranov, and Yao. They defined the notion of path homology of directed graph. And it is kind of a homotopical approach to graph theory, not to graph theory, to graphs. We study graphs from homotopical point of view in some sense. And the definition is quite naive, I think, but it has surprising nice properties. For this homology theory, there is an appropriate Kuhn's formula for the box product of digraphs. It is homotopy invariant in some sense. So we define homotopy for graphs, and it is homotopy invariant. There is an appropriate notion of suspension which shifts path homology. In some sense, it generalizes the homology of a simplicial complex in a sense that for any simplicial complex, you can construct a directed graph whose path homology is the homology of the simplicial complex. There is also a notion of fundamental group satisfying the Hurevich isomorphism. And we together with some students constructed a theory of covering graphs, which also has all these properties which we have for covering of spaces. And let me tell you more about these properties first, and then later I will give you the definition. First, I want to tell you about the Kuhn's formula in more details. And in order to formulate the statement about the Kuhn's formula, I need to tell you, I need to define you the box product of two graphs. If you have two graphs, J and H, then their box product is a new graph whose vertices are pairs of vertices from J and H, such that we have an arrow from a pair. Such that we have an arrow between these vertices if and only if either the first components are equal and there is an arrow between the second components, or there is an arrow between the first components and second components are equal. For example, if we denote by I the following directed graph with two vertices and one edge, it will be a model of the interval in this theory. So, and I will use this notation further. Then the box product of this interval with itself is the following square with 4 vertices and 4 arrows. I need to say here that it is not the categorical product inside of the category of graphs. Actually, in the graph theory, there are many types of products. There are many monoidal structures on the category of graphs. The categorical product is called strong product in the graph theory. And for this particular case, there is diagonal. This is a square together with the diagonal here. But here we use this box product, and it fits better for this path homology theory. And then, okay, and then it is true that for this path homology theory, we have the following version of the Kenneth formula. For ordinary homology of a space, we know that at least of a field, we know that homology of the product of two spaces is tensor product of homologies. And here we have by pH, I denote here the path homology of corresponding graphs, and pH of the box product is tensor product of path homologies. And of course, a similar statement. Of course, we have statements similar to the corresponding statements, not only over fields, over integers, over arbitrary ring. There is also Kenneth theorem, which looks a little bit more complicated, but we still can prove it. Over arbitrary commutative ring, you can develop this theory of arbitrary commutative ring, including field. And here, for simplicity, I write formula over a field, but you can work integrally, for example, and then there will be not only tensor product, but also torsion product.
Can I ask you another question? Modulo, the fact that you haven't defined what is path homology.
Yes, I will define it later. I decided to give you properties first, and then I will give the definition. Yes, first I list some properties, and then I will give a definition of path homology. So it satisfies this Kenneth formula. Then second nice property is that it is a homotopy invariant in some sense. In which sense? We can define one-step homotopic morphisms between graphs. If we first I need to tell you what is a morphism of a graph. In fact, there are two non-equivalent definitions of morphism between graphs. I use the one where morphism can shrink an arrow. So morphism between graphs is a map between sets of vertices such that two vertices connected by an arrow can go to two vertices also connected by an arrow, or to the same vertex. So arrows can be shrinked. And I say that two such morphisms are one-step homotopic if we have the following commutative diagram. So if we have a homotopy, this map is a homotopy, and I is the model for the interval. So it is the directed graph with two vertices and one edge. This relation is not an equivalence relation, but we can consider the minimal equivalence relation such that which contains this relation of being constant homotopic, and then two homotopic morphisms between graphs induce the same morphism on the level of path homology. Yes, vertical arrow is homotopy. The definition of homotopy is an arrow such that this diagram is commutative. This definition is absolutely similar to the definition in the classical algebraic topology. Embedding. Okay, let me. Yes. I is the directed graph with two vertices, 0 and 1. I is a graph with 0 and 1. If you take the box product, it is like cylinder. It is a graph which looks like a cylinder with two copies of the graph J and arrows from the one copy to another copy. And these are two embeddings of these two copies of J inside of this cylinder. So yes, in the homotopy theory, we have a space X, and we consider the product of this space with the interval and embed our space in two different ways. inside of this cylinder, and homotopy is a map from this cylinder. Here, the situation is absolutely similar. We take the box product with this model of the interval and consider two embeddings of J and define homotopy as a map such that this diagram is commutative. It will be homotopy from phi to psi. Okay? Is it a question about definition of homotopy or definition of morphism? First, I define the notion of morphism between graphs. The first comment was about the definition of a morphism between graphs. And now, homotopy is a morphism of graphs such that this diagram is commutative. You can define it in a different way. You can say that two morphisms are one-step homotopic if for any vertex of J, there is, for any vertex of J, phi of J and psi of J are either there is an arrow from psi of J to phi of J, or they are equal. So there's more elementary definition, less categorical in some sense. For any J, you have either an arrow from psi of J to psi of J, or they. Okay, and if we have two homotopic morphisms, they induce the same morphism on the level of path homology. In particular, as well as using this statement, it is easy to check that two homotopy equivalent directed graphs have isomorphic path homology. And homotopy equivalent means that we have a morphism in one direction, another direction, and their composition are homotopic to identity maps. Everything is very similar to the classical homotopy theory. Okay, another nice property is that there is a construction of suspension for graphs which respects path homology in some sense. What is a suspension of a graph? If you have a graph, you just add two vertices to this graph and consider all arrows from these new vertices to all vertices of the original graph. And this is called suspension of a graph, and path homology shifts and this suspension shifts path homology in the following sense. It shifts reduced, but reduced is almost the same as ordinary path homology. This tilde means reduced. Reduced just differs from the ordinary path homology only in 0 dimension. For example, for connected graphs, zero path homology is always one-dimensional, but reduced path homology is 0-dimensional, and this is the only difference. And using this formula, we can construct many examples, many interesting examples. For example, you can start from a graph with two vertices without any edges, and these 2 points is a model of 0-dimensional sphere. These 2 points will have homologies the same as 0-dimensional sphere, only in dimension 0. But then you can suspend this, and this will be a new graph with 4 points. And with arrows from these new 2 points to old 2 points, it will be a graph with 4 vertices and 4 arrows.
And since you are defining homology, 0 element of this algebra is a vertex with no legs, with no edges. Am I right? When you calculate homology, what's the kernel mean?
Kernel?
Yeah.
Kernel of what?
I mean, you calculate homology. Have you defined homology?
Not yet.
Okay.
I have maybe on the next slide. On the
what is the zero element of this algebra of graphs that you're defining? That's
zero element
neutral element of
it.
Is it a vertex? Just a vertex? Okay. Why don't you define homology? I trust that you do.
You mean cohomology? You mean neutral element of cohomology, right?
Sure. Yeah. Unit of element of cohomology. Yes.
It is very similar to the ordinary case, and it is okay. Let's discuss it when I give the definition. But for the moment, I don't speak about cohomology. I speak only about homology. So you need to ask about co-units and co-multiplication. And you can map all vertices of your graph to one vertex, and then yes, this map will induce co-unit. With the same coefficients as here, it doesn't matter. If you work over some fixed field, on the left and on the right, you can take any field and over the same field or over the same commutative ring, it doesn't matter. Yes, so in this way, using this suspension, we can get a model for n-dimensional sphere whose nth homology will be non-trivial. So in particular, in this way, we see that higher path homology can be non-trivial, but in fact, it can be done easier. In fact, path homology can be as complicated as homology of simplicial complex. If we have a simplicial complex K, we can construct a directed graph from this simplicial complex, whose vertices are simplices of this simplicial complex, and arrows are embeddings of simplicial complex. Of the simplicial complex. And it turns out that path homology of this graph, of this directed graph, is the ordinary homology of this simplicial complex. So in some sense, path homology of graphs is a generalization of homology of simplicial complex. But in some sense, it is not interesting case. Okay, now let me give you the definition. This is a definition of path homology. First, we construct some not very interesting complex. We take a graph and we consider the following complex whose components are spanned by sequences of vertices, arbitrary sequences without consecutive repetitions. So they are not paths, nothing like this. Arbitrary sequences of vertices. With this only additional property, that ji is not equal to ji plus 1. And we define the following derivation on this complex. The following differential on this complex. We just, for each I, we just delete the vertex and take the alternating sum. Here we assume that all sequences with repetitions, with consecutive repetitions, are 0. So sometimes here in this sum, we can get a sequence with consecutive repetition. And we think that it is 0. So some summands in the sum can be 0. Okay, it is in some sense trivial complex in the sense that its homology is 0, and it doesn't really depend on the graph. It depends only on the set of vertices. It doesn't depend on arrows. But among these sequences, J0, Jn, among them we have paths, and we can consider the module generated by these paths, and we denote it by an. By a path, I mean a sequence of vertices such that J0, J1 is an arrow, J1, J2 is an arrow, and so on. Yes, I allow this. It is allowed.
Is some, what does it mean? Adding? Is adding set theoretic, or is it what?
We consider free module generated by sequences. We consider all sequences, consider all possible linear combinations of the sequences. So it is a formal sum. And we take a submodule generated by all paths. And it turns out that it is not necessarily subcomplex. This is a problem. How can we solve it? Okay, consider the maximal possible subcomplex whose components lie inside of this K. And we denote it by omega. Omega is the largest chain subcomplex inside of R, whose components lie inside of An, whose elements are linear combinations of paths. There is an explicit formula. It is uniquely defined, this largest subcomplex. There is an more explicit formula for this, but I don't want to write it. And the path homology is the homology of this complex. Of course, you can dualize this definition, especially over field everything is just dual, and you can obtain cohomology also. But let me speak about homology. It is easier for me. Okay, this is the definition. Now I wanted to tell you about coverings also. First of all, I need to say that there is some version. I'm sorry, I don't have time to give all the definitions. There is a version of fundamental group of digraph whose abelianization is the first homology, integral with coefficients with integers. Yes, you asked about coefficients, all this. In this case, it is important that coefficients are integers. And the abelianization of this fundamental group is the first path homology with integer coefficients. And we, together with some Chinese students and one Russian student, developed a theory of coverings of this digraph, so that subgroups of this fundamental group are in bijection with coverings of J. So we have the same statement as we have in algebraic topology. And we also proved, which is more important, what is more important for me, is the following spectral sequence. There is also a notion of universal covering, which corresponds to the trivial subgroup inside of the fundamental group. And we prove that for the universal covering, there is a spectral sequence whose second page is the homology of the fundamental group with coefficients in path homology of this universal covering. And it converges to the path homology of the original graph J. It is important because it gives a relation between homology of groups and path homology. And some computations, which look very complicated on the first glance, can be done very easily using the spectral sequence if we already know homology of the corresponding fundamental group. Okay, and let me tell you about an open question in this area, which I'm very interested in. All the theory goes very similarly. We can also define cohomology. We can also define cup product, and so on. But the question is, what we can't do is to prove that it's graded commutative. In algebraic topology, cohomology of a space is a graded commutative algebra. We can't prove this for the path cohomology. And I think that it is not true. There should be a counterexample. We tried hard to find this counterexample on computer, and we still couldn't find it. Okay, the second theory, the magnitude homology, the magnitude theory. This is theory which was initiated by Tom Lainsner and some other people almost the same time in 2011. And the main notion is magnitude of a metric space. I will tell you about the magnitude function of a metric space, which is a function from real numbers to real numbers, positive real numbers. The second related notion will be magnitude of a directed graph, which is treated as a formal power series. We can replace functions from R to R to formal power series in the case of digraphs. And then I will tell you about the magnitude homology, which is a categorification of this notion. Okay, what is the magnitude function of a finite metric space? It is a sub-function. Again, I don't give definition. I will give it a little bit later. Maybe now, I don't remember. It is some function which is defined for almost all positive numbers, except some finite number of them to R. And it satisfies many nice properties, and it is something, it shares some properties of cardinality, and at the same time, it shares some properties of Euler characteristic. It is something, it is a function, it is interesting invariant of a metric space, which is at the same time something like cardinality of the number of points and something like Euler characteristic. And this definition can be extended to compact metric spaces, but this theory, as far as I understand, this theory is not very nice for arbitrary compact metric spaces, but it is very nice for compact spaces inside of the Euclidean space. Okay, let me give the definition. The definition of this magnitude. You assume that A is a finite metric space. Then we consider a matrix whose components are functions, and this matrix is indexed by points of A. And the AB component of this matrix is a function which sends a positive number t to e to the power of minus t times the distance from A to B. This matrix is almost always invertible. Actually, the first case when it is not invertible was invented by Terence Tao in comments of some blog. So we can take the inverse matrix and take the sum of all components. It is defined almost for all numbers t, and this sum is called the magnitude function of the metric space. It has the following properties. First of all, limit of this function when t tends to infinity is the number of points in A. If we take product of two metric spaces, L1 product of metric spaces, where the distance is defined as the sum of distances, we get product of the corresponding magnitude functions. Moreover, there is a generalization of this notion. They introduce the notion of metric fibration. They try to construct something like model category for metric spaces, so that the magnitude of the fibration is the product of magnitude of B times magnitude of A of the fiber, magnitude of the fiber. Under some additional assumptions on two metric subspaces of a big metric space, the magnitude of the union will be, there is inclusion-exclusion formula for the magnitude. And one more property that I already said, that this definition can be extended to the case of all compact metric spaces, and especially it behaves very nice for compact subsets of Rn. And for these compact spaces, the growth rate of this function is the Minkowski dimension. So this function remembers Minkowski dimension of this metric space. Actually, all this theory can be developed not only for metric spaces, but also for generalized metric spaces, where the distance can be infinite and not necessarily symmetric. What is important is triangle inequality, and the distance from a point to itself is equal to 0. And any graph can be treated as a generalized metric space where the distance is the length of the shortest path. And for graphs, we can also consider the magnitude, but we can develop all this theory replacing functions from R to R by formal power series. And then we will define the magnitude as a formal power series with some integral coefficients. So we get some invariants of a graph, magnitude coefficients, which all behave as, in some sense, as Euler characteristics. So for each L, for each natural L, we have some invariant which behaves like an Euler characteristic, because it is Euler characteristic for some appropriate homology theory, which is called magnitude homology. There is another version. What is defined? Nothing is defined. But actually, if we substitute here Q instead of Q, this is some power series. So that if we substitute Q to the e to the power of minus t, it will be the magnitude function defined on the previous slide. And it was defined. So here on this slide, I define the magnitude as a function from R to R. But it can be also defined, especially if all distances are integer numbers, it can be defined as a formal power series with integral coefficients. So this version of magnitude as a function is defined here on this slide, but there is another version of magnitude, which is formal power series, which can be defined similarly, but we just need to replace this e to the power of minus t by q in this definition, where q is a formal variable. And in this way, we will get a formal power series. And this will be a formal power series with integral coefficients. All these guys will be integers. And it turns out that there is a homology theory which is related to these magnitude coefficients in a way similar to as Euler characteristic of a space is related to Betti numbers, to homology, to ordinary homology. Okay, and let me define you the notion of the magnitude homology. For a generalized metric space A, we define the following, and any fixed number L, we define the following chain complex. The components of this chain complex are pre-modulus spanned by sequences of points such that the sum of distances from A0 to A1 plus from A1 to A2 and so on, the sum of distances is equal to L. And then we define the differential in a similar way as for path homology, but here we also have a lot of zeros among these summands, because if the sequence doesn't satisfy this property, that the sum of distances is equal to 0, we assume it is 0 for this complex. No, it is easier for homology. As for Euler characteristic of a space is not always defined, but homology is always defined for arbitrary space. And here, the same situation. A is arbitrary, a generalized metric space. Yes, and we define this complex in this way. And the magnitude homology of A is the homology of this complex. And it turns out that the magnitude coefficients are related to the dimensions of this homology over any field. In a way, in the similar way as Euler characteristic is related to dimensions of ordinary homology. So, in some sense, the magnitude homology is a categorification of the notion of magnitude. Okay, and now I try to tell you something about these two theories, magnitude theory, JLMY theory, and now the unifying notion, the magnitude path spectral sequence. Before the previous year, these were two absolutely different theories, but Japanese mathematician Yasushi Kasao showed that they are parts of some bigger theory. First of all, he showed that the omega, which appeared in the definition of path homology, is the same as diagonal term of the magnitude homology. So it means that there is a chain complex whose components are magnitude homologies, and the homology of this complex is the path homology. So in some sense, path homology is a homology of magnitude homology. Homology of homology of homology of homology, it means that usually if we see such situation, it means that there is a spectral sequence, some spectral sequence hidden here. Indeed. Actually, Yasuhiko Asao showed...
Can I ask you a question?
Uh-huh.
So when you calculate this magnitude homology, when you apply the codifferential map to a given set of vertices with the length constraint, then this can, oh yeah, okay, so yeah. So when you apply, so yeah, okay,
Yes.
the co-boundary map applied to that, does that image need to satisfy also
no,
this?
No, it doesn't necessarily satisfy this property. And in this case, we identify the sequence with zero.
It's set to zero? Okay, got it.
So in fact, almost always, this summand will be equal to zero. It is not zero only if we have AI minus 1, AI plus 1 are collinear points. In fact, with any graph J, you can associate a filtered simplicial set. Or if you don't like simplicial sets, you can think about spaces, topological spaces. There is a filtered topological space, which is just, it is just an increasing sequence of spaces whose associated homological spectral sequence is a spectral sequence satisfying the following properties. The first page of this spectral sequence is just the magnitude homology. The second page of this spectral sequence contains path homology in its zero row. The zero row, the second page is the path homology, and it converges to the preorder defined by this graph. And I call this spectral sequence the magnitude path spectral sequence. It also has very nice properties. For example, we can generalize the notion of being of the L homotopy. What I defined you is in some sense one homotopy. This is actually another definition in this way. We say that two morphisms of graphs phi and psi are one-step L homotopic if for any vertex J there is a path of length not greater than J, not greater than L, from phi of J to psi of J. These guys are one-step L homotopic. And similarly, we can consider equivalence relation between such guys, the minimal equivalence relation such that this relation, which contains this relation, and it turns out that the L plus first page of the spectral sequence is an invariant of L homotopy equivalence. So I think that all these theories can be unified in one theory, and we should study this spectral sequence and not the magnitude homology and not the path homology independently. This is what I wanted to say. These are some references. Thank you for your attention.
Questions?
So you define this path homology, so you have this graph, and then you construct like simplicial set of admissible simplices and take homology of that.
No, it can be defined via a simplicial set of admissible simplices.
Yes.
What do I mean?
So admissible simplices, like if you have all the edges of part of your graph. I think this is similar to what you said.
I don't really understand your question, but it is impossible to define this homology of simplicial set. It isn't.
It's impossible.
We believe that this is impossible. Yes, this is the first question. Is it possible to define it as homology of a space, of a simplicial set, of some topos, of something else? No, we don't know any other definition except this very elementary definition, and this is a problem. But at least if we prove that cohomology is not graded commutative, then this means that this is impossible. Yes, I think it is impossible.
Question?
Could you define some twisted version of homology over the graph?
A twisted version?
Maybe some shift homology or other geometric objects on the diagram, such as local system, blah, blah.
You mean homology with coefficients in shifts or something like this? As far as I know, it is not written anywhere, this theory. But there are some obvious generalizations. But it depends on what is the definition of a sheaf or coefficients and so on. I know several possible definitions of coefficients, but at least it is not written anywhere. There are some definitions, and actually some people think about how to define this path homology as some derived functors. If we had a good definition of a sheaf and good homology theory with coefficients in a sheaf, then it would give us a description in terms of derived functors. But I don't know such description.
And I'm cheating maybe a little bit because I talked about this with you. Maybe you can also mention Deline's suggestion about this one, this hypercohomology of this sheaf of complexes that might actually give you something that
about intersection homology.
Yeah.
We see some analogy between path homology theory of graphs and intersection homology of algebraic varieties. On some levels, there are very similar formulas. Actually, there is a very naive definition of intersection homology, which looks very similar to the definition of path homology. You can simplicial version of intersection homology. You can consider some chain complex and consider some vector subspaces, graded vector subspace, which is not closed with respect to differential, and you take the maximal subcomplex inside, which is closed with respect to differential. And homology of this will be intersection homology. And there is another more sophisticated description of intersection homology in terms of sheaves, in terms of as homology of some particular complex of sheaves. And we try to find some analogy, but we don't see it.
More questions? So if I'm giving this square diagram and the very beginning, when you have the adjointness of two intervals, if I want to, for instance, calculate fundamental group of a torus from a square diagram, I essentially cannot, unless I forget about the square diagram, but write down simplicial complex for a torus and then calculate path homology of that diagram. Am I right? Or can I kind of have a hard time of seeing how I can compute fundamental group of a torus from path homology, because you said path homology can recover simplicial homology.
Yes, path homology can recover simplicial homology.
What should I do?
To recover simplicial homology, you of a torus, you need to take a simplicial complex. You should present your torus as a simplicial complex, first of all. Then you take so there will be 0 simplices, 1 simplices, 2 simplices. For each of these simplices, you need to take a vertex. You construct your graph whose vertices correspond to simplices, all simplices, 0 simplices, 1 simplices. In fact, you do barycentric subdivision. When you do barycentric subdivision, you consider a vertex for each simplex, and if one simplex is embedded into another simplex, then you take an arrow from this simplex to another simplex. So embeddings of simplexes correspond to arrows in this new graph. In this way, you get a graph whose path homology is homology of torus.
More questions? Okay, if not, let's thank the speaker again. I'd like to make a comment. First of all, thank